In 1869, a group of railway officials watched in disbelief as a locomotive with 2 smokestacks, 2 fireboxes, and no clear front or back prepared to crawl up a Welsh mountain. Critics called it the upside-down engine, a machine so unnatural it should have shaken itself apart before leaving the yard. The mountain's 1 in 40 grades had bankrupted the slate industry, where ordinary steam engines stalled, suffocated, or exploded on curves only 60 feet wide, bleeding money at triple the coal and triple the wages for every load. Yet here was Robert Fairlie's double-ended contraption, the target of press ridicule, union rage, and engineering scorn. Newspapers called it a backward notion, and one columnist sneered that it was a locomotive suited to going nowhere in both directions. If this machine could haul 40 tons up rails where steam could not breathe, it would rewrite everything: the physics of the mountains, the fate of an industry, and the rules of what a locomotive could be. But would this folly survive its trial, or would it be buried forever as Victorian madness? The answer begins with a problem no ordinary engine could solve. Slate quarried from the mountains above Blaenau Festiniog was the best in the world, but every ton had to fight its way down a railway that bent physics to the breaking point. The Festiniog Railway, just under 2 feet between the rails, twisted through hairpin curves only 60 feet wide, barely longer than a city bus, and climbed grades as steep as 1 in 40. On paper, these numbers sounded possible. In practice, they broke machines and men. Conventional steam engines, built for flat ground and gentle turns, choked on these slopes. The higher they climbed, the thinner the air. Fireboxes starved for oxygen, flames guttered, and steam pressure dropped until the locomotive stalled. C.E. Spooner, the railway's chief engineer, described it as suffocating the fire to death, mile by mile. On the steepest climbs, water in the boiler sloshed forward, uncovering the crown sheet, the thin metal that kept the fire out of the crew's lap. If the water dropped, the crown sheet could overheat and explode. Crews learned to dread every lurch, every sudden drop in pressure. The math was unforgiving. A single engine could barely move 20 tons up the mountain. To haul a 40-ton load, the minimum needed to keep the quarries profitable, railway managers had to lash 2, sometimes 3 engines together. That meant triple the coal, triple the wages, triple the risk. 6 men on the footplates, working 6 hours to move a single train just 12 miles. Every extra trip burned through more of the company's shrinking profits. By 1869, the Festiniog Railway was bleeding money. Slate piled up in the quarries, unsold and unmoved. The cost spiral was relentless. Every extra ton required more men, more fuel, and more time, while the price of slate on the London docks kept falling. The geometry of the mountains had become an economic trap. Something had to break, either the railway or the rules of locomotive design. In 1864, Robert Francis Fairlie filed a patent for a locomotive that looked like nothing else on rails. The idea was radical. 2 separate engines, each with its own set of wheels, pointed in opposite directions. A double firebox sat in the center, feeding a boiler suspended between pivoting bogies. On paper, the logic was clear: more fire, more steam, better traction on impossible grades. But the reaction from Britain's engineering establishment was swift and merciless. The Institution of Mechanical Engineers reviewed Fairlie's patent and responded with open disdain. One member called it Mr. Fairlie's backward notion, warning that double fireboxes meant double the risk of breakdowns and double the maintenance bills. In their official proceedings, another engineer predicted, "Destructive oscillations will disintegrate the frame." The idea of 2 swiveling engines, each pulling in its own direction, struck them as an invitation for disaster. The press piled on. The Railway Gazette ran a column calling it a locomotive with 2 fronts and no back, suited to going nowhere in both directions. The Engineering Times published diagrams and equations showing that all that weight hung between 2 pivoting bogies, would slip and slide on the rails. Trade publications dismissed the entire concept as an unnatural contrivance. Union halls filled with anxious talk. Crews noticed the design needed 2 firemen, but eliminated the need for extra engines and turntables. "If one of these takes over, what happens to the rest of us?" a union man warned. Helper engine crews read the writing on the wall. Fewer jobs, less overtime, and a machine that did not care which way it ran. Some called it a threat to their very trade. Fairlie answered every attack with numbers. Articulation, he argued, let the locomotive follow curves that would derail a rigid frame. The suspended boiler kept every pound pressing down on the driving wheels, maximizing traction. The double firebox, he insisted, was the only way to keep steam pressure up where the air thinned out. But the numbers did not matter. In the journals and the union meetings, the verdict was nearly unanimous. The upside-down engine was an expensive joke, doomed to shake itself apart before it ever climbed a mountain. Only a real trial under real loads could settle the argument. Inside the belly of Fairlie's design, everything was built to fight the mountain itself. The central double firebox was not just a curiosity, it was a calculated answer to thin air and long grades. Each firebox sat back to back, each with its own grate and its own fireman. Together they offered nearly double the firebed area of a normal locomotive. 21 square feet in total. That meant more coal could burn at once, drawing in more oxygen even as the air thinned with every foot of altitude. Instead of a single draft, gasping for breath, 2 independent fires roared side by side, feeding a boiler nearly 10 feet long. Heat from both ends drove water to steam with ruthless efficiency, keeping pressure steady at 140 pounds per square inch where other engines sputtered out. But fire alone did not solve the railway geometry. The locomotive's weight, 25 tons fully loaded, hung from a boiler slung low between 2 articulated bogies. Each bogie could pivot up to 15 degrees, letting all 8 driving wheels snake through curves as tight as a 60-foot radius. No rigid frame could follow those bends without binding or derailing. Here, every pound pressed straight onto the rails, turning weight into tractive effort measured at 7,500 pounds, enough to keep 40 tons of slate moving uphill without slipping. Coal bunkers and water tanks rode on the same frame, so every ounce counted for grip. The engineer's controls stretched the length of the cab, so he could walk from one end to the other, and there was no need to turn the engine at the summit. Every system, from the flexible steam pipes to the twin smokestacks, was engineered to keep the machine breathing and moving where the mountain tried to choke it. On paper, the numbers promised a locomotive built for war with gravity and curve alike. All that remained was to see if the machine could deliver beyond the drawing board. At dawn, the platform at Blaenau Festiniog filled with railway officials, quarry managers, and engineers who had spent years doubting every bolt of Fairlie's machine. The challenge was clear: 40 tons of slate, 13.5 miles of climbing and twisting track, no helper engines, no turning at the summit. A stopwatch hung from the neck of the Festiniog Railway's chief engineer, ready to settle the debate in minutes and seconds. Steam built to 140 pounds per square inch. 2 firemen, backs to each other, shoveled coal into the twin fireboxes, each feeding a roaring furnace. The regulator eased open, 8 driving wheels gripped the rails, and the double-ended locomotive rolled forward, trailing a full load of slate wagons. At the first checkpoint, the double pulse exhaust echoed off the slate cuttings, 2 engines breathing in time. The train began its ascent, a 1 in 80 grade with tight 90-foot curves, the kind that had stalled every other locomotive sent up this line. The articulated bogies pivoted through the bends, each half of the engine following the rails without slipping or binding. The pressure gauge barely dipped. Skeptics lined the track, notepads in hand. One engineer who had called the design mechanically unsound was soon sketching the articulation system, shaking his head. By the summit, the stopwatch read 1 hour and 40 minutes, less than half the time of the best double-headed run, and with twice the load. On the descent, the engineer simply walked to the other cab. No turning, no lost time. The locomotive braked the train down 1 in 60 slopes, the 8 drivers steady, the wagons under control. Total round trip was 3 hours and 40 minutes. Coal consumption for the full run came in 30% lower than the old method. The verdict was written in numbers, not opinions. The upside-down engine had done what the experts said was impossible. Today, Fairlie locomotives still climb the same impossible Welsh grades, 150 years after critics predicted disaster. History shows that the machines we ridicule often outlast the ones we celebrate. The next world-changing idea may look just as wrong until it proves unstoppable. What are we dismissing now?